О, и дама не возражает.
Okay, so today our speaker is Anar Dosi, and he will tell us about deformation quantization and noncommutative formal geometry of the contractive quantum plane. Please.
Okay, yeah, thanks. Yeah, sorry for the long name, not long title. Let me try to share my screen first. Okay. Yeah, is that okay in this format? It's fine?
Yes.
Yes.
Okay, yeah. Yeah, okay, yeah, let me start. Thanks for invitation. My best wish from the Far East, China, from Harbin. Yeah, it's a pleasure to have a talk here, to give a talk again. So I'm going to talk about, again, non-commutative geometry of quantum plane, contractive quantum plane. Well, again, briefly introduction. So we know what does non-commutative geometry mean. So again, by geometric object, we mean a couple, topological space and a structure sheaf. It used to be a sheaf of local rings. So, but we are targeting to find out geometry of a non-commutative associative algebra, A. So what kind of geometry stands behind of A? So it's a challenging task of non-commutative geometry. Certainly doing this one, so global sections must be by somehow reduced to original algebra A. So we have an A, we're going to try to generate the geometric space. Once you're turning back global sections, it must be the original algebra A. That's a general philosophy of non-commutative geometry. Okay. Yeah, for example, in algebraic geometry, we have an anti-equivalence between commutative rings and affine schemes so that we can identify them. And in the same way, locally compact topological space and commutative C-star algebras, they are the same in this manner. Well, non-commutative complex analytic geometry deals with the Banach space representations of non-commutative complex algebra. So we're going to fix some finitely generate non-commutative complex algebra, and we're going to try to find out its spectrum. That will be our analytic space. So spectrum used to be what? The set of all reducible Banach space representations. That is going to be spectrum. Well, there will be some sort of exotic topology on X, again, associated with the A. And thereafter, we're going to try to generate some sheaf, Fréchet algebras, so that the global sections would be our original algebra A, or, well, actually, this non-commutative algebra of entire functions. So it can stay close, or it can be exactly the same, like entire functions in generators of A. So not exactly A, so it's a sort of Arens-Michael envelope of A. Well, we know what is that. So non-commutative algebra of entire functions and generators of A is well known in the literature, like as Arens-Michael envelope, introduced by Alexander Yakovlevich. So it's a completion of phi with respect to all possible multiplicative seminorms defined on A. Well, we know, for example, if A is algebra for all polynomial functions on a complex affine algebraic variety, then it's Arens-Michael envelope, just algebra for all holomorphic functions. That's result due to Pekovsky in 2008. For example, if you take the algebra of polynomials, we are getting algebra of entire functions, OCA, of n independent variables. So in the case of a non-commutative polynomial algebra, its Arens-Michael envelope represents the algebra for all entire functions in non-commuting variables generating A. So our main focus will be the quantum plane. So look, that's the meaning of quantum plane. It's a free associative algebra generated by x and y modulo this relation. Q is a complex number apart from 0 and 1. So its Arens-Michael envelope is denoted by OQC2. Well, if you put extra condition like invertible, then we come up with the quantum 2 torus. If Q is not 1, we say that it's a contractive quantum plane. That will be main focus of my talk when Q is not 1. So the Arens-Michael envelope, representing the algebra of non-commutative entire functions in 2 variables, actually, it has a precise description. Again, this key result due to Pyrkovsky again, the same paper. So this is just absolutely convergent power series in 2 variables, x and y. Yeah, pay attention to family of semi-norms, depending on rho. I'm going to plug in here rho. We're all rho. Well, again, this result is true for all q, actually, if q less than or equal 1. If q is more than 1, it can be again reduced to the case of q less than 1. You need just to flip the variables. Therefore, the case q more than 1, less than 1, they are more or less the same. So that's why we can assume just q is less than or equal 1. So for us, it's important q less than 1. Okay, that's a description of Arens-Michael envelope of the quantum plane. They're just absolutely convergent power series. So what's happening if q less than 1? Then Arens-Michael envelope turns out to be commutative modulo its Jacobson radical. This key condition, this critical, so that means all irreducible Banach space representations, as I said in my introduction, that's spectrum of algebra, they're just continuous characters. So that means all irreducible modules, they're just trivial modules generated by means of continuous characters. So look, this is my spectrum X, as I told you, space X. So we can find out exactly what is that. The spectrum of continuous characters, it turns out to be union of 2 complex lines, Cx, Cy. Look, you can accept them like in the C2 plane as an x-axis and y-axis. So that's a union of 2 lines. That will be exactly my spectrum. So in this case, when q is less than 1, we also use this sort of notation instead of this one. Because if you take the quotient modulo Jacobson radical, we come up with the entire functions on the union of 2 complex lines. So it's algebra for all homomorphic functions. So this is an ideal case for us when we can describe precisely the spectrum. We know what is that. And the next step, what about topology and what about the structure sheaf? Okay, so this is my space. This stands for non-commutative analytic space, whose structure sheaf would consist of non-commutative Fréchet algebras extending by somehow my Arens-Michael envelope. But there is a problem here. The problem is the following. So look, this is my algebra, Arens-Michael envelope. We know its spectrum. Actually, there is a bigger algebra. I'm going to explain what is that. So this is embedding here. It's a homomorphism, continuous homomorphism. This algebra is bigger, strictly than this, but its spectrum is still the same X. So this is one of the critical moments in non-commutative theories. So you have a spectrum, but still you can get another algebra with the same spectrum. So this sort of defect of this moment. So let me explain what's going on here. So to restore the geometry that stands for my for my quantum plane, contractive quantum plane, one needs to pass to a certain form of completion. So we need to get something bigger than this. And certainly not just this, so it's important to define some structure sheaf, Fréchet algebra sheaves, and so that global sections would be again, if you take its spectrum, it would be again X. Right? So in this case, global section should be a Fréchet algebra or bimodular. So it's a natural extension of this one. Okay, so it turns out the Arens-Michael envelope is not suitable for this problem, to get some self-satisfactory geometric construction. Well, I will explain this phenomenon, what's going on here. So certainly, Arens-Michael envelope, we know what is that. It's built up like Banach algebra actions, right? So it sort of comes from the functional calculus problem. But from point of view geometry, non-commutative geometry is not suitable here. Well, one historical moment, the same phenomenon was detected in the case of the universal enveloping algebra of finite dimensional nilpotent Lie algebra. We know whose Arens-Michael envelope stands for the algebra of all non-commutative entire functions. Again, in the same theory, to get some self-satisfactory geometry, we completed this algebra. We get a bigger this algebra, that so-called formula radical functions. Well, I can refer to my papers, what happened there. We solved the problem there completely. Okay, now let me start continuously explain this phenomenon and our construction. Again, imagine you have two complex lines, Cx, Cy. So first we focus on the intersection point, 0, 0. This is important. At 0, 0, we have a special stalk. Stalk will be just Cxy, algebra of all formal power series in X and Y. Yeah, first of all, it's just space. It's a Fréchet space. But look at this special multiplication here, sort of Q-formal multiplication here. How we multiply, look, coefficients, Qi and Bt. It's a special multiplication, so-called Q multiplication. So this is an associative multiplication. And my algebra turns out to be Arens-Michael Fréchet algebra. And actually, whatever written here is just multiplication that comes out UQ, our quantum plane. So this natural embedding here, we know, right, is associative algebra. There are polynomials in X and Y. They can naturally be embedded here. And this embedding is just unital algebra homomorphism. So there's a natural extension here with the Fréchet topology, and this algebra, this space, turns out to be OQCX algebra. So this is just non-commutative algebra. We should treat it like a stalk at 0. Now, let's see from 0, look at the direction X. We have two directions here, Cx, Cy, I told you. Well, in the direction of X, I can write down this one like Cxy, right? They're also formal power series with coefficients from Cx and in terms of Y. Well, we know, for example, if you take this power series, I can write down in this shape, right? Hn(x), Hn with this partial sum, fixing n here. So if you get in this shape, you can convert your multiplication at the same, I told you, the Q multiplication. It can be rewritten in this shape again. Yeah, look at here. This is coefficients. They are formal power series. This is a multiplication in the commutative algebra, Cx. But just we need to plug in here Q power I. Adding up. And again, we are getting formal power series in terms of Y. So this is exactly the same multiplication, but just written in this shape, Cxy, and nothing else. So we are saying that we are watching from the origin toward X direction. It looks like that. Well, in the same way, we can look at the Y direction, right? We can write down all our formal power series in this shape, H and Y. Now we are fixing the first index here. And again, the same multiplication, pay attention again, the same multiplication, Q power T now is sitting in the first place. It's a standard multiplication in the commutative algebra, summing up, and power series here with respect to X. Okay, so what have I said concerning the formal Q multiplication can be defined actually in two different ways. First, looking at X direction, then Y direction, right? You're getting two different formulas here. Okay, let's talk about this algebra a bit more. So this algebra has a trivial continuous character, or continuous trivial character is better say. 0, 0. What is being 0, 0? Just annihilating X and Y, right? So it's a character, continuous character. Well, actually, well, Y 0, 0, again, 0, 0 representing the intersection point of two complex lines. So actually, you can prove that this algebra is local. It has only one unique maximal ideal. It's a closed two-side. It's exactly a radical of this algebra. So it's a kernel of this character. And you can also calculate easily the set of all continuous characters. They're just 0, 0, nothing else. So it's a nice local algebra, stalk at 0, representing 0, 0. Okay, now let's switch to concept of topology. I told about this topology in my previous talk, the so-called Q topology. We need to keep both lines with a special topology, both complex lines. So we know briefly what is that. So again, Q less than 1, a subset of a complex plane is called Q spiraling set. If for every X, if you multiply by Q power N, all should be inside of S. So it's so-called Q closed set. Look, this is a Q hull, but including 0. This is important. You should always include the 0 here. For example, if S is a single point, Q hull is a spiraling sequence which tends to 0, including its limit point. Look, this is a Q hull. Well, right, there's a Q rolling here and moving toward the 0. Q hull here. Okay, a subset is said to be a Q open set. It should be open set first and should be Q spiraling set. Then we are saying it's a Q open set. For example, all complex plane is Q open. Empty set is also assumed to be Q open. So the family of all Q open subsets define a new, this family defines a new topology, Q topology. This topology is weaker than the standard topology of the complex plane. But at 0, they are the same. I mean, the filter base at 0, they are the same. Because if you take the small disk, whatever disk centered at the 0, just Q open set. So neighborhood filter base, they are the same in both Q topology and the standard topology. They are the same. But for different points, they are not the same. It's much weaker. For example, but pay attention, 0 will be generic point. This is a non-Hausdorff topology. 0 is dense here because every open set contains 0. So if you take non-zero point, you can calculate its closure. Closure will be this tail of the sequence starting Q minus K. It goes to infinity like that. This is a closure of X. So CQ satisfies the X and T zero, and it turns out to be a reducible topological space, which is not quasi-compact. So it's just some space, topological space. Well, concerning compactness here, so if K is a compact set in the standard meaning, then it's a quasi-compact, but not necessarily Q closed. Almost nothing here can be closed. For example, all disks centered at the origin, they are quasi-compact, but none of them the closed subset of CQ. Because whatever containing zero, it turns out to be dense, so weak. Well, for example, if you take the point, if you take it closer, it's not quasi-compact. You can see here it's not quasi-compact. It goes to infinity like that. Anyway, so some non-empty subset is quasi-compact if and only if its Q-hull could be quasi-compact. But the good side is every quasi-compact is bounded automatically. Okay, this is our Q topology of the complex plane or complex line. Okay, now let's look at the standard sheaf. We know the standard sheaf of holomorphic functions. And we have an identity map, which is continuous because the topology is weaker. We can draw my sheaf to this topological space, direct image. It's just the same sheaf on this topological space, CQ. So for every open set, it's just the same. The family of semi-norms, they are the same, but only K should run over all two compact sets. They define the same original topology, but pay attention, every open set, let me recall again, it contains the zero. So as a Fréchet algebra, they're the same, just OQ is OU. This is our sheaf related to our new topological space CQ. Yeah, but concerning stalks, both, they have the same stalk at zero. This is quite normal, right? Because the filter neighborhood is the same at zero, but for non-zero point is quite different. So look, this is my stalk at non-zero point. So these sheaves are actually quite different sheaves. So for example, if you calculate the stalk at zero, is not local. It's not local at all. Okay, so this is our sheaf. Now I need a bit filtration of the sheaf for my future construction. That sheaf, it has the following filtration of closed ideal sub-sheaves. Look what I'm doing. Take an open set, Q open set. It contains the zero. And let me pick up all the functions so that z power minus d times fz would be holomorphic. So that means I can pick up some functions which is vanishing at zero, including all derivatives till to d minus 1. So that's exactly my ideal, MDU. There's a closed ideal of this sort of functions, right? Well, you can easily see that what is that, right? It's just principal ideal. So MDU is just principal ideal generated by z power d. Look, that's my principal ideal. And actually, this one is isomorphic, topological isomorphic with original algebra, OQU. Look, if you look at this mapping, that exactly implements a topological isomorphism of the Fréchet space. But pay attention, Fréchet space here, not algebras. And you can also easily construct a continuous projection onto this subspace, the closed subspace. So our algebra is decomposed like that. This is a closed subspace and polynomial subalgebra generated by 1z z power d minus 1. So this is a topological direct sum of the subalgebras, this one and that one. Okay, so I get a new sheaf. So this is a sheaf also, right? Fréchet space sheaf, not algebra. And let's use notation, OQD, the so-called D shift of our original sheaf. And we have this decomposition. Look, this is actually a subsheaf here with this sort of decomposition. If D is 0, we are getting original sheaf, right? So we have a standard sheaf on this CQ topological space, and we can talk about all these D shifts. D is non-zero integer here. I mean, non-negative integer. Okay, so now we have two lines, as I told you, Cx, Cy, two directions. We can equip both with the Q topology, and union can be equipped with the final topology so that both embeddings are continuous. So that's exactly my Q topology on this spectrum, CXY. So upon sets, we mean the union of two UX, UY. So every Q upon set, it may have two branches, UX, UY. One of them can be empty. It's okay. Okay, so what happened here? CXY turns out to be union of two reducible components, CX, CY, whose intersection is a unique generic point, 0, 0. So this is our exotic topology form, the spectrum CXY. Okay, now let's switch to construction of sheaves, Fréchet algebra, because we wish to have some sheaves, Fréchet algebra, non-commutative Fréchet algebra sheaves. Again, in the direction of x, what I'm doing, in the direction of x, I have this sheaf, OQ, and I have this constant sheaf, C, formal power series, CY, is a Fréchet space. So let me look at this, their projective tensor product. So I'm getting a sum sheaf here. Okay, what is that? So if you look at the sections of UX open set, because I'm talking about only direction X, CX. So this is just the formal power series over OUX. Well, we know how to construct semi-norms. That's easy. Look, I can get this because it's a direct product topology here, so I can get the finite sum here. Getting these standard semi-norms and adding up from 0 to n. So this is my Fréchet space. This is my Fréchet space in the direction of x. Okay, so actually, this is a Fréchet algebra sheaf. Look at the multiplication. Again, let's take the two formal power series. Let's multiply exactly in the same way as I told you in the formal series, in the direction of x. Well, pay attention, this multiplication makes sense. This is a holomorphic function. This is also a holomorphic function, but my ux contains 0, so it contains all these qix's. So that's why this multiplication makes sense. Look, the q hol of every point is inside of ux. So this is a standard multiplication from the commutative algebra, holomorphic functions. And look at here, I can generate multiplicative semi-norms. Just accept K to be a Q compact set. You can easily prove that if Q compact set, all the semi-norms will be multiplicative. So there's a nice Arens-Michael Fréchet algebra sheaf on the X direction. Okay. Well, let's link to our Arens-Michael envelope. Look, this is, again, the same standard homomorphism. If you take the polynomial, ordered polynomial, you can rearrange in this shape, right? That's always possible. If you rearrange in this shape, so you're going to be inside of this algebra, and this map left ux, this is a continuous algebra homomorphism. So that's it. So this, my sheaf, is actually Arens-Michael Fréchet or QCX algebra sheaf, or by module, it doesn't matter. And you can also calculate spectrum, continuous characters. They all continuous characters will be exactly u of x. So you know, as in the standard theory, so every character can be defined by means of points, ux, from the set ux. So we link to our Arens-Michael envelope in the direction of x. Okay, let's do exactly the same in the direction of y. You can easily guess what is that, right? Again, now we have a formal power series in terms of x. Multiplication exactly the same. Just q switch to first variable and first place. Again, this one makes sense. Linked homomorphism with the Arens-Michael envelope. Again, you can get this formal, the polynomial, ordered polynomial, you can rearrange in terms of y's and x here. So this is a continuous algebra homomorphism. Again, there's a nice sheaf in the y direction. Spectrum, again, uy. So in both directions, we have nice Fréchet algebra sheaves, extending our Arens-Michael envelope. Okay, so we can draw both sheaves to our CXY, to our union, in the standard way. So we have how many sheaves? We have left sheaf, right, and this is also constant sheaf, Arens-Michael envelope, and this is also algebra constant sheaf, right? So more explanation, this is not so hard to prove it, decomposition theorem, so you can easily see that zero terms here in the formal power series is actually our original commutative subalgebra. And the rest is Jacobson radical. So we have a topological direct sum here. The same in the y direction. So look, the radical is just the rest, starting from 1, the power series. The same is here. So again, this is not hard. This decomposition theorem, both they are so simple, is so straightforward. Okay, now let's pick them up both. Let's see what we got. So take open set, Q open set. This is my x direction. This is my y direction. This is my intersection point, 0, 0. So we have stock here, Cx, y. This from the left, this from the right. And we can link them. How you can link them? Look, you take the formal power series, coefficients, they are holomorphic functions. But for coefficients, you can write down Taylor series expansion, standard Taylor series expansion. Look in terms of the derivatives. As a result, you're getting the numbers here, the complex numbers, and look, you're getting formal power series. The same from the right. If you get this holomorphic functions and formal power series, just get this Taylor series expansion, you're getting formal power series. Actually, both are continuous algebra homomorphisms. So you can accept them like formal evaluation of the stalks at 0. One from x direction, the other one from the y direction, right? That's quite natural. So what we wish, we need to have something compatibility, right? Because we wish to find sort of section of a union. So by somehow, these two sections must be compatible here. 0 is only intersection point. Okay. Okay, yeah, let's pick up all the picture again. So this is Arens-Michael envelope, constant sheaf. This is stalk at 0. This is X direction. This is a Y direction. So we got Fréchet algebra sheaf morphisms. This is a commutative diagram. I mean, I'm not commutative, it's just diagram here. From the left, from the right. Okay, yeah, this diagram makes commutative. If you start from the Arens-Michael envelope, if you rearrange in terms of X or in terms of Y, if you eventually move toward the formal power series, you will get the same, right? By uniqueness expansion of a polynomial. It's not so hard to see it. So this is a commutative diagram of Fréchet algebra sheaves or sheaf morphisms. Okay, now let's construct our sheaf. So what we are doing? So we focus on sections from both directions that are compatible at 0, right? This is so-called a fibrate product. So we define a new sheaf to be fibrate product, left, right, over this one. I will explain what is that. So, well, roughly speaking, so you can feel that as an intuition. So we need to pick up two sections that are compatible at 0. Look, that's exactly written here. It's a new sheaf. They must be projections, both directions, so that this diagram must be commutative, right? The so-called fibrate product of two sheaves over this constant sheaf. So look, that's exactly the definition. So we need to pick up two sections, F and G. This is a compatibility condition. So both formal power series must be the same at 0. Look, they were coefficients. They must be the same. Yeah, pay attention to flipping the indices here, K and I and K, and factorials moves down here. Look, so this is our sheaf. And in this case, again, we have a natural homomorphism from Arens-Michael envelope to our sheaf. This also will be natural Fréchet algebra sheaf morphism. Okay, yeah, let's look at, forget about everything, relax for a while. Let's look at the general case. What is that? So everyone knows what has been fibrate product. It's a well-known construction. Just briefly say what is that in the category of Fréchet algebras. So if you want two two morphisms in this category, X to Z, Y to Z, S and T. Look, S and T. Sorry. Yeah, so fibrate product is just pullback of the morphisms S and T in this category. So it should be, again, Fréchet algebra with the special two projections, so that this diagram must be commutative. But not just this, right? It should be sort of universal. It's a pullback, we are saying. So it's a universal injective property. If you have another diagram like that, W, Fréchet algebras, another diagram, then there is a unique morphism. W should be linked to our fibrate product. So that, well, the natural condition should be satisfied. All diagrams should be commutative, right? So it's a universal injective or just injective object in this category, right? In the special category of the morphisms, S and T. That's called fibrate product of Fréchet algebras. Well, construction is so easy. If you wish directly, yes, please. So X, Z, Y, Z, just pick up two couples from the Fréchet sum so that S of X equals T of Y. So from two different directions must be the same. They should be compatible. So you can easily prove that is a closed subalgebra in the direct sum. So that's exactly our fiber product. Okay, examples. For example, if you wish to understand what is meant sheaf, standard sheaf of holomorphic functions on the union of two complex lines. This one exactly means fiber product. The copy of sheaf on the x direction, on the y direction, but their compatibility means that they must be the same at zero. Look, F0, G0 from the sum, they should be equal because zero is only intersection point. They must be the same. So this is our algebra. Look, this is our new sheaf on the union of x and y commutative. Spectrum again will be U. One can easily prove that spectrum continuous characters again will be U, nothing else. Okay, this is a simple, nice example of the fiber product. Okay, let's switch back. Look, this is our sheaf fiber product, non-commutative sheaf over constant sheaf. This is a commutative stuff. Look, Ux, Uy, now over C. Actually, these two diagrams can be linked. For example, you can move from this one till to here. We know in our decomposition theorem, this part was just zero term, it's just projection. There is a natural projection from here to here. And if power of y is zero, you're getting this zero term. And the same is here. The zero power of x is going to be here. So there are natural homomorphisms. So we can easily connect both. But from Cxy to C, we have a trivial character, 0, 0. So for these angles, all sides are linked. Then there must be a natural homomorphism from Fq to here, right? By universal injective property. So look what I want to say. So look, this projection, 0. This another projection, 0. And this is 0 character. All these free maps or free morphisms, they define a new morphism from non-commutative stuff to commutative stuff. We're just getting F0, G0. So the challenging problem is not so a trivial problem to understand what will this kernel. Is it true that kernel is going to be radical again? Do we have the similar picture here? And can we describe it? So the first task, how to describe this sheaf. What is that? Okay, to have a precise description, you will see here some special construction that's called deformation quantization. Actually, having just sheaf OQ, we can, by deforming it, we can get this sheaf. Look how. But remember I told you about this D shifts. So we had a standard sheaf. We can talk about this D shift in the X direction, in the Y direction. Actually, this both shifting, D, they also, we can also link them in this by means of special map, STDT. Look, it's not just calculating at 0, it's just calculating D's derivative, dividing by D factorial. Again, this is a map from the left, this is from the right. So we can talk about, again, fiber product, OC, but with the special, these morphisms. Again, if D is 0, we are coming back to original commutative sheaf on the union of two lines, Cx, Cy. Okay, again, they're so-called continuous evaluation linear maps. Again, pay attention, here is all about linear maps, not homomorphism, linear maps just. Okay, so you can easily verify that. So do you remember I told you this is an isomorphic copy of OQ? they were this sort of map. And on the y direction, it's also isomorphic copy of this. Look, this sort of map is a z-plane, w-plane. And actually, all these connections, they are compatible with all these connecting maps, ST maps. So look, if you calculate a 0 for this map, you're ending up with SD. And the same T0 with TD. So whatever maps, they're all compatible. So that's why there is quite a natural map. Let me show you. Look. So OQD on the union. Again, this is a topological isomorphism of the Fréchet spaces on the union of CX and CY. So on the union, on the spectrum, we have OQ sheaf and all its shifted versions. And they are isomorphic copies of the OQ. Okay, now let's formulate our first non-trivial result. So again, let's U Q upon set. I told you about this map. So this map turns out to be a retraction in the Fréchet algebra category. This one means this commutative algebra is embedded into our algebra as a closed subalgebra, commutative closed subalgebra. The rest exactly Jacobson radical. So it's a topological direct sum. But not just this, radicals can be decomposed like that. Direct product of the shifted versions or shifted versions. So this identification is a topological isomorphism of the Fréchet spaces, not algebras. It's just Fréchet space representation here. The space of all continuous characters, again, is reduced to U. So this is also nice. So we are not losing spectrum. The spectrum is the same as U. So now let's analyze this result. So what I want to say here, what is that? Okay, so what we got? We have the commutative space, or if you wish, commutative analytic space, CX, Y, OQ. This is a commutative stuff, or commutative geometry, if you wish. So we are taking the structure sheaf, OQ, shifting them up over all non-negative integers, then fold them up like a direct product. Oh, look, this is exactly our sheaf of non-commutative Fréchet algebras. So this is so-called deformation quantization. Look, it's providing you exact formula, what to do. You have a sheaf, shifting, and direct product. As a result, you're getting non-commutative analytic space. So that's exactly the geometry that we were looking for. So this sheaf is OQCX algebras. And the most important part, we are not losing spectrum. Spectrum is the same. Look, spectrum is the same CXY. In this case, sheaf has a decomposition, is a commutative sheaf of subalgebras, and the rest is a radical. So we have some geometry here, non-commutative analytic space. The only moment left to understand what will be our global sections, what they are. So now I'm going to show you that global sections is larger than the Arens-Michael envelope, but not much, a bit. Now you will see why it's so happening. So let me explain now. Do you remember in my introduction, I told you about the formula of Perkovsky's? So precise description of the Arens-Michael envelope. They were power series of two independent variables. But look, I can weaken this condition. Let me look at those formal power series so that the partial series, they are convergent. So, well, let's analyze from another point of view. Remember, the spectrum is a union of two lines. So let's accept just over x line is entire function, over y line is also entire functions, and that's it. And then look at the formal power series like that. So this is my new semi-norms. They are weaker than this. So that's why we're getting a larger algebra here. But this is quite natural. So if since spectrum is a union of two lines, as an entire function, we can accept something which is entire over x-axis, entire over y-axis, and it must be compatible. Yeah, by the way, pay attention, Hartog's theorem is not applicable here. You could think that maybe by Hartog's result, it should be analytic in both variables, but that's not true because f is not a function. F is just formal power series. And look at this example. Look, this is a formal power series with this sort of terrible coefficients. First of all, as a series of two variables that diverge, it's not an entire function in two variables. Look, just plug in rho equals 1, you will see that this series is absolutely divergent. I mean, it doesn't converge. But if you look at this partial sums, I mean, with respect to x or y, you will see they converge. Look, that's exactly this sort of functions they pop up here in our new algebra, which is quite natural from point of view geometry. Again, so that this one explains why we don't like here Arens-Michael envelope is not suitable to this problem. Arens-Michael envelope is suitable for different problems like functional calculus, but for geometry, to restore the geometry, look, we need something like that. The special formal power series. Okay, so this is done. First part done. Let me end up with the second part. I wish to say a few words about topological homology or Alexander Yakovlevich. So, well, again, here we have a key result, again, by Perkovsky, like embedding is a localization in the sense of Taylor. So what's the meaning of that? If you can use the Takhtajan resolution, you can get nice resolution for this algebra, for the Arens-Michael envelope. Look, whose differential can be written like in this matrix, this compact form, like in the matrix shape. L and R are the left and right representations. Okay, we knew about this resolution. So if you take any algebra or QCX algebra, certainly non-commutative, well, as an example, look, we said so far, in the x direction, y direction, FQ, this is a stalk at 0, all of them, they can be examples of this sort of algebra. Then you can easily calculate resolution for this algebra. Just apply this functor to your resolution, tensoring left and right. You will end up with a similar resolution to A. So you're getting free A bimodal resolution for A. Look, this complex is admissible. So from homological point of view, we have a nice resolution. We can do all calculations here. Okay, so let's start, for example, let's start with the left Fréchet OQX module, X. So what is the left Fréchet module? You can easily understand, like, what is that? That means we come up with the two continuous linear continuous operators, continuous linear operators with this sort of relation, right? Once fixing T and S, you can get this module. So if you take right module or QCX module Y, let's say all our Fréchet modules, So we say that y is in the transversality relation with respect to x if all homology groups, they are vanishing for all k more than or equals 0. In this case, we write y, yeah, probably this notation due to Taylor, but again, you can see in the book of by Alexander Yakovlevich. So there is a bit more general definition, one functor in this sort of relation, transversality relation with respect to module, when all the derivatives, they are vanishing here. But anyway, this is a special case. What is right module in the transversality relation with respect to left module, if this one happens. Yeah, for example, you can apply it for trivial module, C gamma. You know, the gamma is a continuous character. So if this one happens, we say that gamma from the resultant set of this couple T and S. So complement will be spectrum. Let's say Taylor spectrum. Well, again, calculation of this Taylor spectrum is not so hard because we have a resolution. So we can easily apply this moment to our resolution. Let's see. So homology groups can be calculated by means of our resolution, and we'll end up with the nice complex, parametrized complex over our CXY, the general union of two lines. Look, this is my differentials, D0, D1. Gamma is a parameterization. So certainly the spectrum has two sides, X direction, Y direction. Look, we are writing X direction, Y direction. So this is our Taylor spectrum of this couple S of T or just left module. Okay, look at the second result, the key result. So suppose X is a left Banach module over a quantum plane. Again, that means we have a couple of bundling operators with this sort of relation. And let's fix a Q domain. So it's a Q upon set and should be domain, just connecting the standard sense. Oh, look at this analog of the famous Taylor's result on analytically parameterized Banach space complexes. Certainly I'm using this result, but there is more stuff here, more technical stuff. So this algebra is a right module in the transversality relation with respect to X, if and only if UX intersection with the right-hand side is empty. The same result for in the Y direction. UY is empty. Now look at this one. This one is interesting. So the stalk at 0 is in the transversality relation of X, if and only if 0 is not inside of the spectrum. Yeah, there's a nice result. On the left-hand side, we have a topological homology. From the right-hand side, we have something very geometric stuff, like open set spectrum. But our target, can we say the similar result for our sheaf, connecting both directions? Well, you know the meaning of that I told you. It's all about exactness of a certain sequence. We are tensoring, the result should be exact. So suppose X direction exact, right direction exact, lower side is exact. Can we conclude that our fiber product, again, is going to be exact? So sort of taking fiber product is an exact functor or not? Yeah, in general, answer is no. Again, let's switch to general case just briefly. I will explain. I told him like French general. So let's see, what is that? Just like take this two like angles like that. In the amorphism in the category of Fréchet algebras. So we can easily explain what does morphism mean, right? So we need to connect Z1 to Z2, X1 to X2, Y1 to Y2, all must be compatible or commutative. Look, free morphisms. And then we can easily define the morphism of the fibered products, right? That's easy. It's just standard stuff from category theory, how to define the morphism. Okay, so you can use, again, universal injective property. So we can also talk about morphism, exact sequence of morphisms. Look, the couples of morphism, S1T1, S2T2. Okay, let me say. Look, this is my exact sequence. Let's take S0T0, S1T1, S2T2, and this connection is an exact sequence of morphism couples. If you take their fibered products, there's going to be left exact image of U1 will be closed, but you may have a cohomology group here in H2. And it's not surprising, like the cohomology group H2 is by somehow linked here. Look, this is a precise description of the second cohomology group. Oh, look, it depends on what? First of all, we have S1T1. Image S1T1 means sum of images S1 and T1. We can draw it back. We have a connection map between Z0 and Z1. This is L0. We can draw it back and look at the quotient S0, T0. So this gap will be exactly my second cohomology group. So in general, this we are failing. So fibered product is not an exact functor. So you can fail here in general case. Well, but we have a powerful theorem, decomposition result for our sheaf. So nonetheless, using our decomposition theorem, we can prove this result. So X left Banach module given by unoperated couple, U a non-empty Q domain. Then again, in the left-hand side, we have a transversality property. On the right-hand side, we have quite a geometric property. U intersection spectrum should be empty. So they are totally equivalent. On the left, we have a topological homology. On the right, something simple geometric stuff, right? Yeah, this is my second central result. And you can see, like, so the geometry is important. Yeah, let me stop here. Yeah, geometry d'important. Thanks for your attention. Let me stop here. Yeah, okay.
Thank you very much. Questions, please, remarks. Well, I have a question about your sheaf FQ. The question is it acyclic over CXY? I mean, so if we take the homology, so
yeah, it should vanish. I think not, because I'm not sure it's a sort of affine stuff, but I don't know exactly. I think it's not true, because if you compare to algebraic geometry, it seems it's not affine. It's just two cover. It looks like a union of two affine. It has a certain cover of two affines, but I'm not sure. It seems not. But I didn't investigate. Yeah. Yeah, it's interesting questions. Thanks for that. Yeah, the problem not, because comparison to algebraic geometry is not it should not be affine. That's a problem, because to prove something like that decomposition theorem, I mean, like deformation, is technically really hard. It's so complicated. You know, it's, well, you can feel, right? We have two affine subsets, and they have an intersection point. Intersection is dense. So too much techniques here. Yeah, I don't know. Sorry.
Yeah.
That is a good question. Yeah, it's better to investigate. But I think no. But my feeling is that is not true. It's not so. Okay.
Okay, thank you. More questions,
Okay.
please. Well, if not, then let's thank the speaker. Thank you, Anar, for the very interesting talk.
Yeah, it's my pleasure.
Well, next week we'll have Oleg Alstov also from Harbin, and next week, well, I'll send you. Maybe we will have some change of time, but in any case, I'll send you executive information a bit later.
Oh yeah. So, sorry for time. So we are in China. It's about 11. So, but it's okay. So for me, it's okay. Oleg was worried about it, so maybe it's better shift up. But anyway, it's okay for us.
Thanks.
We can say no, stay, no problem.
Mhm.
Okay.
Yeah.